All right, now a mini lecture in chapter 18 on electron donating groups and electron withdrawing groups. So we looked at this a little bit in chapter 16 in relation to the Diels-Alder reaction. And so after this, after you watch this, maybe go back and review some of that about the Diels-Alder. So when we discuss an electron donating group or an electron withdrawing group, we're really talking about the effect that that group has on a pi system it's bonded to. All right, so I've got two examples here. We've got phenol, we've got acetophenone. Phenol's got an oxygen directly bonded to the pi system, so each of these molecules has a pi system in a benzene and one substituent. And so let's do the top one first. So the oxygen, you guys should look at an oxygen as a polarized bond, right? So the CO bond is polarized so that the oxygen's partial minus and the carbon's partial plus. This is an inductive effect. We call this induction, right? So induction is just the effect of electrons, or the behavior of electrons, the effect of a substituent on the electrons via sigma bonds. By resonance, we get a resonance effect then. If you draw a well, how about you do that? Hit pause and draw at least one resonance structure of phenol. Don't draw just moving the double bonds around. Use these electrons, use the oxygen lone pair in a resonance structure. Okay, hopefully you did that. If you're going to use the oxygen lone pair, they're going to push down into the benzene ring. And we get a resonance structure that looks like this. Right? This oxygen winds up with, it's still got one lone pair there. Now there's a lone pair here and a negative charge, and you still have those pi bonds. You can move these electrons, here. I'm going to leave off the lone pair. Now I'm just going to show the charge. You can move that there, move that there. All right, and then we can get back to where we started from. Get back to phenol. I'll put the lone pairs in here. Okay. All right. So what you would expect from these lone pairs is the oxygen is actually, what you would get from the resonance structure is that the oxygen's actually by resonance pushing electrons into the benzene ring. Right. So this oxygen is making the benzene more electron rich. And if you think about it, if you had phenol act as a base or a nucleophile, you'd expect the ortho, the para, and the ortho positions to be the most basic positions. And that's exactly what we find. We're going to find this in the electrophilic aromatic substitution reaction, which is going to take up most of our time in chapter 18. All right, and we would call this then, we would call OH an electron donating group, because by resonance, it's pushing electron density into the ring. And so an electron donating group is going to be any atom with a lone pair So an electron donating group is going to be any atom with a lone pair that's directly bonded to the pi system. Okay, so now you'll probably see the pattern. There's electron donating groups and electron withdrawing groups. You might look at acetophenone, it's got a ketone here, and you see an oxygen with lone pairs, and you're like, oh, there are lone pairs there, so it's a donating group. It's not. The atom with the lone pair is not directly bonded to the pi system, right? The substituent, this group, is bonded to the pi system through this carbon, which does not have a lone pair. So go ahead and do the same thing. Hit pause and draw at least one resonance structure where the benzene electrons interact with the carbonyl. Okay, so the oxygen is strongly electron withdrawing by induction, and so we're going to end up here with a cation there there, right? That's one resonance structure. We've taken these 2 electrons, moved them there, moved the pi electrons and the carbonyl up onto the oxygen. Then we can just delocalize the positive charge around the ring. And then finally, we can re-aromatize and get back to our starting point. Okay, so now if you look at this, if you look at the direction the arrows are going, the carbonyl is pulling electron density out of the pi system. And we're going to call this an electron withdrawing group. Okay, so if when you draw good resonance structures, the arrows are going away from the pi system, the group bonded to it is an electron withdrawing group. If the arrows are by resonance are going toward the pi system, it's an electron donating group. And the same thing here. If we expected acetophenone to act as a base or a nucleophile, we'd expect the ortho and para positions to be the least nucleophilic, right? They're positive charges. They have partial positives. On the other hand, if we expected the benzene to be an electrophile, that is, nucleophiles would attack that, with an acetophenone here, we'd expect nucleophiles to attack the ortho and para positions. And phenol, we'd expect the ortho and para positions to be the least reactive with electrophiles. So, an electron withdrawing group so an electron withdrawing group is going to be a group that has a partial positive or positively charged atom directly bonded to the pi system. Right? If you think about the carbonyl, that carbon, the sp2 carbon of the carbonyl is really strongly partial positive. The oxygen's partial negative. If excuse me, if this was a nitro group, that nitrogen would be positive. And now the last thing I'll put in here, and we'll go over it some later. As always, the halogens are an exception to this rule. Right? The halogens are, by electronegativity, a little electron withdrawing. By lone pairs, they're electron donating, and they kind of do both.